For this slab, I'm going to open an IGES neutral format file, and so I'll open it from my computer and I'll select motor mount IGES file. And so here we see our parts. I might want to set this as the home position. I'm going to rotate around and set that current view as home, and then I'm going to measure one of the edges on here and make sure that it's the size that I expect. So I'll measure this size and I see that it's 10.24 inches, and I'll come over here and make sure my document setting is in inches. I'll then expand the assembly, and I see that I have a knuckle shaft, a left bracket, and right bracket. Make active the right bracket, and then I'm going to expand the bodies, and I see that I have 35 unstitched bodies. I'll select the first body, and then I'll go down and holding the shift key I'll select the last body, and then I'm going to go to the inspection and then I'll say validate those surfaces, and I will tell it to repair any issues that it might find. I'll say okay to that, and it converted that into a solid body with no issues found. I'll then do that with the left bracket, so I will expand, drill down to the surfaces. I'll select the first one, hold down the shift key, select the last one. I'll go to inspection, validate, okay to that. No issues found with that one. And then I'll go to the knuckle shaft and I will expand the bodies, select the first one, hold down the shift key, select the last one. I'll do inspection, validate on that. No issues found. So now I have that one as a solid body. Let's go back, make the top level active. Then I want to apply my material to these three components. So I'll go to the knuckle shaft and I'll go to physical material. I'm going to set this to ASTM A36, and I'll drag that up into my model and I'll apply that to my part. While we're here, let's go also and get aluminum 61. So I'll go through and I'll find aluminum 6061, and I'm going to do that at 6061 T6 cold formed. Let's drag that and drop that onto this part, and I'll drag it and drop it onto this part. Alright, then we'll go through and verify. So I will go to the properties. This should be ASTM A36, and I'll verify the properties of this one. And this is aluminum 6061, and I'll verify the properties of this one, and again aluminum 6061 T6. Alright, I'll save it, and then I will go to the simulation. I want to do a static simulation. I'm going to put a fixed constraint on this face right here and this face right here. So I'll do constraints, I'll do fixed on this face, and I'll say okay to that, and I'll do the same thing to the other side. Then I'm going to put a load on this face and on this face. So I will go to my loads and I will select this face. Now we're going to put a total of 40 pounds on this face. Now the question always comes up, if I select both of these faces, is that a total of 40 or is that 20 spread across these two faces? I'm going to suggest that you do it both ways. You select both faces with 20, and then you select one at a time with 20 and compare the results so that you understand if it's doing it as 20 spread across the two faces or 20 and 20. So I know that if I do it as 20 and 20, I have a total of 40. So I'll let you do the other experiment. Alright, then I'm going to mesh the parts, and actually before I mesh it, let's define the contacts between here and the brackets. So I will go to contacts, any gap less than 4/1000ths of an inch, bond that together. So I'll do generate. I'll expand, so I have my materials over here, the steel and the aluminum. I will expand the loads, so I have 20 and 20, and then the contacts I have bonded, and if we select those it shows us where the bonded contact is, here and over here. Okay, our constraints. We have fixed constraint on this side and fixed constraint on this side. Then we'll go ahead and mesh the part, and I'm going to edit the mesh settings before I start, and let's bring this down, let's say to about 2%. It gives us a warning that it could take a long time to do that. And then I will mesh the part. Alright, I'm going to analyze this two different ways. So I'm going to right click on study 1 and I'm going to say clone that study. But I'll go back and make study 1 now my active study. and I will run the analysis. And I'm going to run that locally. We see we have a safety factor that is greater than 5. I will go to the stress, and I see that the high stress areas are in this area right in here and in this area right in here. So when we have this motor, let's say it's driving a belt, we might want it to actually bend slightly when it first starts the motor rather than breaking something, or if we have a chain hooked to the motor so that it doesn't break the chain. So we might actually intend for this to bend some right at the beginning. I will then go to the displacement. Let's exaggerate this displacement so that we can see it more clearly. And so I'm going to go ×2. Okay, so I've got this coming down, bending in and towards the inside. Let's even increase that some more. Okay, so it's bending down and towards the inside. Let's go ahead and animate this. So I'm going to animate that and play the animation of the bending. So really, for our real mechanism, we have a motor attached here and here. So the feet of that motor, the fasteners, go through these holes and hold this face and this face against the bottom of the motor. So these two parts actually can't bend towards the inside. They can only bend down. We don't want to put the motor in there though, because it would take a long time to mesh the motor, and we're not really testing the motor. We're testing these two brackets and this knuckle shaft. So let's go to our second study, and this time I'm going to put a constraint on here to keep these from bending towards the inside as though we had the motor on here. So frequently in FEA analysis, we idealize our study to make the computations as simple as possible. So I'm going to put in a frictionless constraint on this side, and I'll do a frictionless constraint on the other side. That will keep these faces vertical so that they can't bend towards the inside. I'll then run my simulation again. We see again that we have a safety factor over 5, and I will go to the stress. Again, our stress is in this area, in here and here. I will then go to my displacement, and I'm going to exaggerate that deformation again ×2. And now when I play this simulation, when I animate it, we see that these brackets just bend straight down. They don't bend towards the inside. So we've represented this as though we had the motor attached to the brackets. If I go to Inventor to open up the IGES file, I'll select open, and then I want to set Inventor to open solids or surfaces. Because we have a IGES file, we very likely have surface bodies within the file, and I will find the units from the source file, and then really important here to tell it to stitch together the surfaces into solid bodies. So then we'll say OK. And we see that it did bring in the surface bodies. I'm going to rotate around this way and set this as my home position. So I'll right click on the view cube and I'll set that as my home position in that orientation. Then I want to make sure that I don't accidentally move these components, as right now if I drag it, we see that it can move anywhere in space. So assembly constraints aren't preserved through neutral file IGES or step format translation. So I'm going to ground these free components so that I don't accidentally move those. But these grounded constraints don't transfer over into the analysis environment. I then want to open each one of these files individually, and I will tell it no, I don't want to recognize features, but I will right click and tell it to repair bodies, and I'll tell it to find any errors, select everything, and make sure I have the green check mark, and do that for each component, and also assign the materials for the components. Other than that, everything else is the same in Inventor that it was in Fusion 360. I'll open up the Lab 11 files in SolidWorks. The first thing I want to do is, before I open up any neutral format files, is I'm going to go to System Options and Import, and I'm going to make sure that Enable 3D Interconnect is turned off for the purposes of these labs. So I want to completely separate the part files from the neutral format files. Alright, so I've verified that 3D Interconnect is turned off. I'll then do Open. I'll set my file types to IGES, and I'll select the motor mount IGES file, and we'll open the components. Again, the first thing I want to do is fix these components so that I don't accidentally move them. So I will right click and select fix for each one of these three components. I'm going to turn on shaded with edges for better visibility, and I want to measure one of these edges to make sure that the units were translated okay. And so I'll go to the evaluate tab and I'll do measure, and I see that that is 10.24 inches, what I was expecting, but I also want to make sure the units on this problem are inch units. So I'll go back to my options again and I'll go to document properties, and I'm going to set this to ANSI standard, American National Standard Institute, and for the units I'm going to set this to inch pound second units. Then we would apply our materials, and actually before we do that, let's open up each component and run a quality check on that. So I will open up the knuckle shaft. I'll right click on the imported node and I'll run import diagnostic and verify that there are no errors with each of the parts. I will then assign the materials and then go into the FEA analysis, assign the contacts, bonded contacts between the components, and we can set that to do that automatically. Assign our constraints, and then we'll put a roller slider constraint on the side here to keep these sides on this side and this side vertical. So other than that, it is the same process as in Fusion 360.